Origami is the ancient art of Japanese paper folding. For years, it has been used to create stunning works of art. But origami has also been used in more surprising ways, like car airbags, stents, and even space exploration.
What we want in space are large structures, not necessarily massive, but large, which means you can make them out of thin materials. And wherever you can make them out of thin materials, you can use origami to fit them in these rockets.
Many space projects have used the folding principles of origami. The solar array wings on the ISS use a Z folding pattern, and the Mars Phoenix lander used a fan-folding solar array called the Ultraflex.
Because the biggest rockets we have right now are only about 5 meters in diameter, we have to come up with a way of folding up this very large structure into space so that we can launch it inside a rocket. And once it gets to space, it can unfold itself. And origami is one mechanism by which we can do that because it gives us the underlying mathematics of how large, thin sheets fold up.
One origami project currently in development at NASA's Jet Propulsion Lab is the Star Shade, which is essentially a big star blocker. Have you ever tried to take a picture of someone when the bright sun is beating down on them? All the detail gets washed out. This is the same problem astronomers have when trying to image exoplanets. Currently, astronomers detect exoplanets indirectly using a shadow technique called the transit method. For an Earth-sized exoplanet orbiting a sun-like star, they can't be imaged in detail because the stars they circle are much brighter than they are. This is where the star shade comes in, to help block that bright light to better help astronomers learn more about these mysterious planets and look for biosignatures for life.
One of the ways in which we're thinking about suppressing the starlight is using something called star shade, which is a very large external occulter that flies in front of a space telescope and blocks out that starlight so you can image that really faint planet right next to it.
Sounds easy enough, but the star shade is roughly the size of a baseball diamond.
Because the star shade is so huge, we have to come up with a way of folding up this very large structure into space so that we can launch it inside a rocket. And once it gets to space, it can unfold itself.
Which is where origami comes in.
So this is one of the candidate fold patterns that we had for the inner part of the star shade, what we call the optical shield. It's got a very deterministic shape when it's folded up, so we designed it to have this shape in which it can account for the thickness of that blanket. You can mathematically define how this sheet of paper is folded up, and the way it unfolds is like that it creates these very nice spirals inside the folded structure. It's quite remarkable in its simplicity.
This giant space flower may seem simple in design, but not in implementation. The star shade will need to unfold with millimeter accuracy. Once opened, thrusters will move the craft through space, positioning the star shade between the star and the space telescope. With the star now being shaded, the telescope can image the planet in detail to find out whether conditions for life exist. Origami has been practiced on Earth for years, and scientists will continue to draw inspiration from it to help package big space structures more efficiently, from solar sails that use sunlight for propulsion to sunshades for telescopes like Gaia and the James Webb once it launches in 2019.
We can take these ideas from origami and apply them to spacecraft structures that way.
Because when it comes to the future of space exploration, if we want to think big, we also have to think small.
It's now mathematically proven that you can pretty much fold anything, says Robert J. Lang. Robert J. Lang is a very important figure for the rest of the reading, so please bear that in mind. So, this Lang person says that it's now mathematically proven. What this means is that now origami is mathematically proven. You can explain origami by using numbers, by using math. Okay, that's a fact. And so, since you can explain origami using numbers, you can pretty much fold anything. Because you can prove origami using math, you can create any form of craft with origami. He quit his job as a physicist to follow things full time. So he's done. He ended his career as a physicist, and now he is doing folding things. He's making origami as his new job. What is a physicist? A physicist is a type of scientist who studies and teaches physics. Okay, Lang actually worked for NASA, but now is devoting his full time, his 100% on origami. We basically solved how to create any appendage or shape. It kind of links on to what he has previously said. So because origami is now can be explained by using numbers, they can create any form of shape and form. They can fold anything. So we basically solved how to create any appendage or shape. Appendage basically is a small part of a larger piece, usually referred to arms and legs. So we know how to create any form of arms and legs or shapes thanks to the fact that origami now can be explained using mathematics. Flap, how to make a flap. Okay, flap is the folded part. Okay, and if you fold a paper like this, you can create a flap. And if you unfold the paper, you would see such a crease, such a line. If you fold some more, you can create a thinner flap. And it kind of resembles a circle, or at least a quarter of a circle, right? Flaps can come from edges, from the corner, or half a circle, or even from the interior of the paper. You can see the full circle, first circular shape, right? So these circular shape, they all become a flap. And what does a flap do? They can create appendages, arms and legs and such. In the 1990s, origami experts came to the realization that each appendage of a paper figure consists of a folded flap of paper. So it's not that far distant in the past that these origami designers, these professionals in origami, they realized, they became known, they were enlightened to this fact that each appendage of paper, like the part of the paper that makes arms and legs of a figure, right? They are consists of a folded flap of paper. Okay, so the folded flap of paper can be made into appendage. Okay, that's what these origami experts realized in 1990s. The flap is made from a circular section of the original square. Okay, the flap, where does it come from? It comes from a circular section. The reason I showed you the earlier slide is to explain this part. A quarter of a circle, or a half, or the full circle, these all circular section, you call that circular section of the original square, because origami paper is usually a square shape, right? These later on are made into an appendage or an arm or leg. This insight was crucial, Lang says, because it allowed origami experts to relate origami to a very old mathematical puzzle. This realization, this insight that you can pretty much make any type of appendages with the circular section, this insight was very important, crucial. Because the reason why this was important is because This knowledge allowed origami experts to relate to this very old mathematical puzzle, and that's what we're going to find out what that is. What can that be? So this is a part of a old mathematical puzzle. It's called circle packing. In geometry, circle packing is a study of the arrangement of circles or equal or varying sizes on a given surface such that no overlapping occurs and so that no circle can be enlarged without creating an overlap. That's a circle packing. In other words, how to put as much of the circle in a given space. Okay, that was the old mathematical puzzle or problem. They connected the folding process to a mathematical method for putting spheres into a box or circles into a square. This is kind of explaining what this mathematical problem is. So these people connected the folding processes to mathematical method, this type of method. And who are they? The origami experts. They connected folding, creating these flaps to this old mathematical puzzle of putting spheres into a box, like the picture in front of you, or circles into a square. Okay, this is a circle packing. This insight also allowed these artists to create complex creatures with numerous arms and legs, as well as lively scenes such as musicians playing instruments. Okay, so this insight, this realization also allowed this creation, okay, of animals with numerous arms, multiple arms, because they realize the number of flaps can directly lead to the number of arms and legs. Okay, so now these origami artists can now create all sorts of creatures and things that they only could have imagined in the past. So as well as not just these creatures with multiple arms and legs, but also scenes such as musicians playing instruments like these. These flaps not only are created into arms and legs, but also these pointed parts in musical instruments. They all can, the flaps can be created into these as well. Perhaps more important, however, it led some of them to discover significant technological applications of paper folding. Maybe it is saying that it is more important than what had been, discovered, such as making numerous numbers of appendages, arms and legs. It is more important than that discovery, and that discovery is the application of paper folding, origami into technology, applying these realization into science of actually creating things to help our daily lives. For example, engineers working on the design of car airbags asked Lang to figure out the best way to fold one into a small space. So here's an actual example of how origami or the technology or techniques of origami have been implemented or applied into a real life situation or real life technology that actually benefits us. So engineers who are designing car airbags, these group of people went and went and visited, approached Lang to give his insight about how to put this like big airbag into a small tight space. Because Lang is an expert in origami, and what does origami do? What is the key function, or what's the unique thing about origami is that it puts a big thing into a small space, right? So that's why this group of engineers who are designing car airbags went to Lang and asked him how they could put this large airbag into a small, relatively small space. He realized that his design for origami insects would do the trick. He is Lang, of course. He realized that his design for origami insects, the way he designed his origami insects, that design will do the trick, meaning that will be applied, that will help solve this problem of putting this car airbags into a small space. It was an unexpected solution, he says. What it means is that he didn't anticipate this. It was a delight discovery. He never imagined that his origami insect, design for his origami insect, will help design a car airbag.